very happy to have Robert Huang visiting. So Robert did his PhD at Caltech. One cannot be learned in the quantum universe, so thanks.
Yeah, thank you, Thomas, for the very nice introduction. Today I'll be talking about what cannot be learned in the quantum universe. This is going to cover two of our recent work. One is random unitaries in extremely low depths with Tommy Schuster, Jonas Hefferkamp, and also how to construct random unitaries with Vermima. So we all know that in order to accelerate science, it is very important to understand how we can design efficient algorithms to learn in the quantum universe. And some of the basic tasks include trying to learn properties of quantum systems, trying to learn the Hamiltonian describing our many-body dynamics, etc. However, like what Thomas was saying, for some basic aspects of the world, we have tried really hard. So my collaborators and I have been thinking very hard on designing efficient learning algorithms for learning some very basic properties about our world, but somehow we just failed to design an efficient algorithm to learn them. And as a result, this raises these interesting questions that I wanted to talk about in this talk, which is, are there some fundamental basic aspects of our universe that we can prove using cryptographic tools and information theoretic tools that they're fundamentally hard to learn? Or equivalently, one can ask the same question, but if one takes a more experimental perspective, we can ask fundamentally hard to measure. Or if we take a more philosophical notion, fundamentally hard to see or hard to feel, which is some words that have been used in the pseudo-randomness literature. So the outline is roughly as follows. First, I will start out, or the first part of my talk would be on various results regarding what are some simple looking problems that actually are provably hard to learn. And then the second part, I would like to talk about how we establish and prove these results using various tools related to random unitaries, pseudo-random unitaries, etc. So let me begin with the first part, where I would like to talk about how time is hard to learn, causality is hard to learn, and topological order is hard to learn. Let me begin with time, which is one of the most fundamental aspects of our universe. So one way to formalize this question of can we feel time, which is a very high-level, vague question. One way to formalize it is as follows. Of course, there are also other ways of formalizing it. But one way that seems quite natural to us to formalize it is the following. Suppose that there is some unknown unitary that arises in either nature or in experiments or in some control devices, etc. Suppose we don't know what this unitary is. But we can access it in the sense that we can maybe evolve our system under it. Maybe we can probe this unitary, like we can initialize some state, evolve under it, and so on. And furthermore, it's guaranteed that the unknown unitary is one of the two cases. It's either a very short time dynamics. So let's say we have a 1D system, and it's a short time dynamics, meaning that the unitary can be generated by a nearest neighbor interacting dynamics, for example, a quantum circuit of low depths. Or it's this crazy object, which is exponential time dynamics. Think of it as it's a generic unitary sample from the entire space of unitaries, also known as a Hall-random unitary. And it's well known that for a Hall-random unitary, this unitary will require exponential time to generate. So we can see that in these two cases, on the one hand, we have short time dynamics, maybe constant or polylogarithmic time, very short compared to the system size, which is low entanglement. Or on the other hand, we have this exponentially long time dynamics that generates a huge amount of entanglement and complexity and so on. And we can ask the question, suppose that we have this unknown unitary, can we efficiently distinguish between them? So one way to formally ask the question, how can we feel time, or can we efficiently feel time, or efficiently measure time, is the following, which is suppose that this unknown unitary is either this short time or exponential time 1D dynamics. Can we efficiently distinguish them? However, this question itself is still not well defined enough. In order to define it properly, we have to talk about what is the subject we mean. So here we're going to consider sort of the kind of strongest imaginable entity that can arise in the future, which one could think of it as, so we call it quantum agent, but one could think of this quantum agent as just a very smart experimentalist that have capabilities over all quantum technology. So it has a full-fledged fault-tolerant quantum computer. It also has very powerful quantum sensor that can capture all kinds of quantum information in nature, and then also a fault-tolerant quantum memory that can store quantum information. So what this quantum agent could do in accessing this unknown unitary is as follows. First, it can initialize itself in some initial memory state, so quantum memory state, and then it can generate some input state, possibly entangle with itself, and then throw that input state into this unknown unitary. So it can just evolve that input state using the unknown unitary. And then afterwards, the quantum agent can utilize, say, quantum sensors and quantum transducer to take the output state and pull it back into its quantum memory. It can then analyze that quantum information that it has obtained from evolving under the unitary, or it can just store there, and then initiate the next experiment, so the next query to this unknown unitary. So the quantum agent, from a complexity theory language, is essentially a quantum query algorithm that can access this unitary oracle many times. So it can then produce some inputs, use quantum sensor to retrieve it, and then analyze it in its quantum memory. And finally, over many rounds of interaction, the quantum agent will output either in short time or long time. And we say it can distinguish it efficiently if the answer is correct, say with high probability. So now we have formally defined the whole question. We can then start to look at this question again. And let's say we start out by focusing just on classical dynamics. So let's say this unknown unitary is actually a unitary correspond to classical dynamics. So it's just a classical transformation that we would like to probe. And we'd like to understand if quantum agents can efficiently distinguish between short time versus exponential time classical dynamics. So what's the answer for that one? So actually that has been well studied, and the answer is very easy. Or the answer is very simple, is that it's very easy to distinguish between short time versus long time. So here's a pictorial proof of this fact. So what the agent needs to do is just the following. So it put in two bit string. So it first put in, let's say, spins, every spin is pointing up. Or in the second case, the first spin is pointing down and then up everywhere else. So it just puts in either this or this. So first it can put in this state, evolve under the unknown dynamics. So now in this case, it will be a classical dynamics. And then afterwards, it produces some output bit string. So output state A. It do the same thing, but for this other input state, getting another output state B. And what it essentially have to do is just compare the two output states. So for classical dynamics, if it's a short time evolution, then we know that by flipping the first bit in the initial state, it will cause the output to only change locally. So let's say in this case, only the bits that are close to the flip will actually change. And all the rest would be exactly the same because of causality, of light-cone argument. So just from this, one can see that if one saw most of the bits are the same, like let's say all the bits that are far away from the flip are the same, then we know that this is a short time dynamic. So it's very easy to see that a short time dynamics is short time in classical systems. And on the other hand, if this is an exponentially long random classical dynamics, when we flip the first bit, the bits will just change completely. So some of the bits to the right hand side would also change. And as a result, that gives a very simple test for whether it's a short time dynamics or a long time dynamics in classical systems. Just by testing causality. So if we go back to this question, can quantum agent distinguish short versus long time in 1D classical dynamics? The answer is very simple, it's just yes. This quantum agent can efficiently tell time. We also don't need a quantum agent, which is a classical agent, just putting in this through bit string will also suffice. And now we can also ask the same question, but now for quantum dynamics. So now this unitary is truly some dynamics generated by quantum evolution. Then what's the answer for this question? So somehow surprisingly, by combining these two works that I described earlier, we can prove the following theorem, showing that under standard cryptographic conjecture, no polynomial time quantum agent or quantum algorithms can tell apart between a very short time 1D quantum dynamics from exponential time 1D quantum dynamics. So somehow when we now just change it from classical dynamics to quantum dynamics, the answer certainly becomes no. So if we look back to this example, we can see that in order for classical dynamics to look like a truly random scrambling object, one would need linear time. One would need a time that allows this to kind of propagate through the whole system because of Lycan argument. However, somehow in 1D quantum dynamics, this time can be sped up exponentially. So one only needs polylogarithmic time. It's basically just polynomial in log. The precise exponent is something like log squared in order to behave random. So if we do the same experiment as this one, if we do the same experiment, what we essentially see is that both of the output states that comes out of it suddenly look like completely random states, that there's no relation between them, or at least from all kinds of efficient experiments that we can do, there's no relation between them and this very shallow quantum circuit would just look like an exponentially complex object. So somehow this suggests that while time is sufficiently measurable, at least we can easily distinguish very short time from longer time object in classical dynamics. In quantum dynamics, things scrambles, or observationally things scrambles exponentially faster than classical systems, causing time to be very hard to learn. And similar argument can be extended also to talking about learning causality, learning causal structure. So a more concrete example is as follows. Suppose that we have some unitaries that is generated by quantum dynamics that are either consists of just short range interaction or consists of long range interaction. So think of it as we have some short range interacting systems and now we evolve under some short time. Or we have these long range interacting systems where there's all-to-all connections and we evolve for some short time. It's not hard to see that by evolving under a short time, the two systems will have very different causal structure. So in the short range interacting systems, if you look at each qubit, the causal cone, like the light cone of each qubit, will just contain things that are nearby under a short time. However, if we have a long range interacting system, then for each qubit or each spins, the causal cone might just already contain things that are very far away, because of the long-range interaction. So the two have very different causal structure in a short time. If we evolve for a very long time, then they have the same causal structure, which is the light cone contains everything. But if we just evolve under some short amount of time, then the two should have very, very different causal structure and entangling patterns and so on. And one could ask the similar question, like, can we design some efficient learning algorithm that can efficiently learn the causal structure and efficiently tell this vastly different causal structure apart? And what we essentially show, or essentially using related ideas, one can prove that this is actually hard. So there's no way for any efficient quantum experiment to tell apart between unitaries generated by short range interaction or long range interaction. And this is more formally stated as the following theorem. Under the same cryptographic conjecture, we can prove that no polynomial time quantum agents can tell apart short versus long range dynamics generated in a short time. And hence they cannot tell distinguish causal structure. However, I would also like to note that if we now consider a more powerful observer that have the ability to reverse time, so it can evolve forward in time, so it can access unitary for evolution, so applying U, but it can also apply U inverse, so U dagger. Then such a observer can actually now distinguish the two easily. But of course, this observer is much more powerful because it has the capability for reversing the entire evolution, which in various many-body physics situation seems a bit too powerful. Of course, in some cases, especially when the unitary is already known, then we can reverse the evolution. But if the unitary is unknown, then reversing it is hard. And a third result is considers topological order. So for those of you who are not super familiar with topological order, let me just give a very simple introduction. So recall that in geometrically local shallow quantum circuits, we know that they can only generate short-range entanglement because it's very shallow, so only things nearby are being entangled. So example is like, suppose I have this 1D systems with a depth of D, then the entanglement entropy in the middle cut will be bounded by D. So if D is small, then the entanglement entropy is small. As a result, these geometrically local shallow circuits cannot alter long-range entanglement. So one example is to consider, say, product state. The product state has no long-range entanglement. Now if we apply some shallow 2D circuit on top of it, then the output state will still have no long-range entanglement. On the other hand, if we have a torical ground state that has been proven to have long-range entanglement, now if we apply a shallow 2D circuit on top of it, the output state will still have long-range entanglement. So physicists has considered these idea of topological order or topological phase essentially to be defined as an equivalence class. So we say two states have the same topological order if they have the same long-range entanglement structure, or another way to say it is they can be connected by shallow circuit. So these families of states that can be generated by applying shallow 2D circuit to product state are known as short-range entangled state, and they have trivial order because they don't have any long-range entanglement structure. On the other hand, this family of states that can be generated by applying shallow circuit onto torical ground state are considered states with topological order. And an open question in the intersection of machine learning and quantum physics asks the following. Kind of like trying to classify cats and dogs. So if people are thinking of trivial order as cats and topological order as dogs, if you ask the question like, if you're given copies of a state, so we don't know what the state is, but we have many copies of it, it's either from the trivial order or from this topological order family. Can we design an efficient algorithm, like an efficient classifier, that can tell if the state psi is topologically ordered or not? So over the past 10 years, there have been hundreds or even thousands of papers that propose new algorithm for it. So people have proposed ideas from using quantum neural networks to establish this. People have also proposed ideas for using some classical machine learning technique for answering this question. However, all of these proposals are heuristic in nature and they often fail in some cases. And hence, prior to this work, it was still an open question of whether this is doable or not. So for some of the more optimists, like machine learning optimists, they might think that, oh, we should be able to come up with a good machine learning algorithm for doing this. But what we essentially found is that even though shallow 2D circuits cannot alter topological order because it doesn't change the long-range entanglement structure, it somehow can hide it. And essentially what we show is that if we just have some random topological order state or some random trivial state, both states will look like exponentially complex Hall random state. And as a result, there's no way for one to distinguish between them. And here's the third theorem, which says that under the same conjecture, no polynomial time quantum agents can learn properties that are invariant under shallow circuit. So this can be generalized. It doesn't have to be topological order. As long as there are some properties that's invariant under shallow circuit, then it's not learnable. So together, these results essentially establishes that some of these very fundamental aspects of our world, like time, causal structure, topological order, are all unlearnable. Which seems kind of strange, because in all of these, for example, time and causal structure is pretty easy in the classical world. But somehow when we move to the quantum world, it becomes way harder to do. So for the second part of my talk, I would like to dive into the ideas behind these results. So what are the tools that allows us to claim these seemingly outrageous claims? So first, let me provide a background on random unitaries. So essentially the way we do this is we're going to utilize random unitaries as a powerful tool to understand and establish these computational honors of learning various fundamental physical properties. But before going into that, I would also like to say a few words about random unitaries and some of the other implications of some of our results. So random unitaries have been pretty central in quantum information technology because people have found various use cases for it. I would say one of the most popular places where random unitary arises is in demonstrating quantum supremacy. So in the random circuit sampling task, we essentially create a random quantum circuit which generates some random unitaries that form some design, and then by measuring the output state, we can produce classical bit strings that are classically hard to sample. Random unitaries have also been used in various benchmarking technique, like in randomized benchmarking, which is apply a bunch of random unitaries, and the nice thing about it is that essentially scrambles the noise, so everything becomes white noise. In the context of classical shadow, we also utilize random unitaries in a very crucial way. So in order to learn some unknown quantum system, what we would do is we will apply some random unitary to the quantum state and perform measurement. And by analyzing the information contained in the measurement outcome, as well as the unitary that we apply, we can now predict many properties of the quantum state using very few measurements. These objects, random unitaries, have also been very crucial in understanding complex quantum many-body dynamics. For example, in the context of quantum neural network, using properties of random unitaries like two designs, one can establish this famous phenomenon known as barren plateau, which says that the training landscape of quantum neural network has this very flat, exponentially flat cost function and only a kind of a narrow gorge boundary. And in the context of black hole physics, people have also been utilizing random unitaries to understand these extreme physical systems. For example, the famous Aquino-Susskind conjecture, also known as the fast scrambling conjecture, states that black holes are the fastest scramblers in nature, with a scrambling time of log n. And over the past decade, people have now been equating scrambling as the formation of these random unitaries. And that have been very useful in matching gravitational calculations, etc. So what is a truly random unitary? A truly random unitary, also known as Haar random unitaries, is a unitary that is sampled uniformly from the entire unitary group. And it's well known that these generic random unitaries will require exponential time to generate, because they contain like exponential complexity and there's too many of them. So if we write them out as a quantum circuit, it would correspond to an exponentially deep quantum circuit. And there are some various properties. For example, by applying this unitary to some product state, it would create very high entanglement. When we apply it again to product state, it would generate exponential state complexity. But as a result, the Haar random unitary is also too complex to actually be physical. There's just too much complexity inside of Haar random unitary. So one thing that people have also been thinking about from the more physics context is that while Haar random unitaries are exponentially complex, so they're too complex to be physical, can we still model physical systems with Haar random unitary? And an interesting question that arises in that context, which relates to the kind of the unlearnability results that I described earlier, is this question. can we somehow model some short-time dynamics that occurs in physical reality? Can we model it, or can we show that they are essentially indistinguishable from these exponential time random unitary?
You keep on using the word dynamics.
Yeah.
When I think of dynamics, I think of Trotter's dynamics or a Taylor expansion. You've got some probably fixed Hamiltonian in time and fixed circuit structure.
Yeah.
And then on the other hand, you're talking about short-term versus exponential time random circuits. You seem to be equating the two. Is that only in a hand-wavy sense to motivate your story, or are you really saying that shallow random circuits versus hard random circuits can be viewed as dynamics under some exponential time or exponential time?
Yeah, so if one takes Hamiltonian, like time-dependent Hamiltonian dynamics,
time-dependent you can do it,
then one could do it.
but not with fixed time.
Yes, if it's time-independent, then there's still a gap.
Yeah, with time-dependent obviously you can do it, but it's like changing the entire time. It's
That's
not
right.
changing in a physical way, really.
That's true, that's true. But we'll address that in the upcoming work. So
Okay.
yes, but in these results we didn't address that. So now we're kind of just talking about time-dependent, short-time, time-dependent dynamics, where the Hamiltonian could change arbitrarily. So actually, from the physics context, one also arrives at the same question as before, and it's essentially the same question that we were asking earlier. So, and in terms of the existing literature, usually people consider two common notions of indistinguishability. The first one is known as K-design. Maybe some of you have heard of the word. So K-design means that the quantum agent cannot distinguish this unitary from Hall random under any K-query experiment. So it can access U K times, and it cannot distinguish it. On the other hand, the notion of pseudo-random unitary, PRU, concerns quantum agents that can perform arbitrary number of queries as long as it does everything in polynomial time. So these are the two common notions that have been proposed and studied in the literature. So another way to ask the same question is another equivalent way to ask the same question is the following: Can K-design or can pseudo-random unitaries be generated or formed in a 1D system in a very short amount of time? If the answer is yes for this question, then it immediately implies that quantum agent would not be able to distinguish 1D short versus exponential time quantum dynamics. So, kind of, in order to establish some of these unlearnability results, it boils down to asking this question of whether K-designs or PRU can be formed in a short time. So now, after reviewing a bit of random unitaries, let me dive into pseudo-random unitaries, because that's going to be the more important thing. Because here, we can see that for K-design, it only concerns with experiments that queries at K times. But in order to establish these true unlearnability results, we need to talk about PRUs, which concerns with any quantum agents that runs in polynomial time. So previously, there have been a lot of works that establishes random unitary, the existence of random unitary designs. So some explicit construction includes just taking a bunch of 2-qubit gates and then padding them in a brickwork structure. However, what about PRUs? So a priori, it's actually not clear if they exist. So PRUs are essentially polynomial-sized random quantum circuit that are computationally indistinguishable from exponential time Hall random unitary. So a priori, people don't know if such an object exists, and only until recently, last year, with Fermi-Ma, we established a theorem proving that under the standard cryptographic conjecture that quantum secure one-wave function exists, then pseudo-random unitaries exist. So quantum secure one-wave function just means there is some function, like a hash function, where you can put in some arbitrary input and you'll produce some outputs, but now that computation is efficient. But now given an output, computing the input that associated with it, the image or the pre-image, that's hard. That's the definition of one-wave function. And under that standard definition, or under that standard conjecture, we can prove that PRU exists. And the proof essentially utilizes this construction by Tony Mecker, Alex Bramba, Hsin and Yuan. It's called the PFC construction. It's a very simple and elegant construction. The construction looks like this. So the C just corresponds to a random Clifford circuit. And the F here corresponds to a random phase operator. So it's fully written out like that. It just means when you put in some classical bit string, it will apply a +1 or -1 phase based on X. And then the last component is a random permutation, which just, when you put in a classical input like a bit string, it will just randomly permute it into another bit string, pi of X. So all of these three objects looks very classical. Because Clifford circuit are easy to simulate classically, F is just a classical function, P is also just a classical permutation. So all of these things look very classical, but what was quite interesting is that we can actually prove that the combination of P, F, and C is actually indistinguishable from exponential time Haar random unitary. The general idea behind this proof looks like the following. So on one hand, we have these Haar random unitary, they're exponentially complex. On the other hand, we have PFC. So it's a much more classical object. But how do we relate them? The key idea for proving the indistinguishability between Haar random and this PFC is by constructing a form of a hyper-efficient simulator of Haar random unitary. So I think before diving into that, I'd like to talk briefly about an idea for essentially generating an exponentially complex random function. So in classical computer science, there's this well-known idea called lazy sampling. So if we have some exponentially complex, truly random function that also have exponential complexity, just creating them is going to take exponential time. But actually, there's a way to simulate them in the sense of the following. So whenever we query an input, f of x, then at that point we sample the output, and then we store it. We store the output corresponding to that. And the idea is that initially we just store nothing, and only when we query it, we would draw a random sample. If we now query the same point, we would just take the original output and report it. But now, on the other hand, if we query a new point, then we will again sample a new outcome. So the idea is that in this lazy sampling, we will have an environment that stores a collection of, or record a collection of randomly sampled objects, and then we will be essentially using that in order to simulate a truly random function. This hyper-efficient simulator of Haar random unitary can be intuitively thought as that. So if we have a quantum agent, like an instrumentalist that wanted to access Haar random unitary, which itself, if we wanted to just write it down, it would be exponentially complex. So there's no way one can actually write down a Haar random unitary. But what we constructed is the following simulator that utilizes an environment to simulate Haar random unitary. So everything happens here. So the quantum agent can only see things in the system space. But there's an environment which is initialized with an empty set. So think of the environment as it starts out with nothing. So there's an empty set S, and that's the initialization of the environment. And now, whenever a quantum agent queries a Haar random unitary, so initially it would just be querying a U, it would just evolve under U, produce output, and then retrieve. Now, how we essentially simulate it is that when a quantum agent queries it, it actually now implements this simulator. It's a unitary transformation that can be efficiently implemented on quantum computers that entangle the environment as well as the system. So the formula might look a little bit intense, but let me just show it in action. So initially, the environment will just be an empty set. And now, when the quantum agent generates some input, throw it into the Haar random unitary. So let's say it just generates some superposition over different x, and then throw it into the Haar random unitary. The simulator, what it does is that it now essentially performs this operation onto this empty set. So what it essentially creates is the following. So if the simulator sees x1, so if the quantum agent throws in x1, the simulator would now generate a superposition over all y1. And now the y1 will be entangled with the environment. So one can think of it as it's generating like a bell pair between the environment and the system qubit. So x1 will actually get stored into the environment and it generates an entanglement, like an entangled bell pair. And now the corresponding output, this y1, like 1/2 of the entanglement or 1/2 of the bell pair will now be returned back to the quantum agent. And now when it queries a different input, like x2, what the simulator would do is it would now again generate approximately an entangled bell pair between the system and the environment. So the environment continues to store these jumps from x1 to y1 and then x2 to y2, and it always creates like a uniform superposition over these y's, while matching these like distinctness condition. So now the thing will retrieve, and what we can essentially show is that this simulator, which we call the path recording oracle, is actually close to the Haar random unitary. And the way we showed that was essentially like we look at this PFC construction, and then we consider the C to either be a Clifford or be a truly random, like a Haar random unitary. And then we showed that actually in both cases, when we write out or simulate this PFC construction using this like lazy sampling idea, we can essentially create this hyper-efficient simulator of Haar random unitary. And when this C is not a Clifford but a Haar random unitary, that's just equivalent to the other side. And as a result, the 3 are equivalent, or the 3 are approximately the same. And that's like the very high level idea for how we prove that PRUs do exist. But now that just says there are some polynomial sized quantum circuits that are indistinguishable from exponential time. But in order to get all the results that I talked about, we need to prove a final ingredient, which we call the gluing lemma. So the gluing lemma states the following. Suppose I have 2 random unitary. One is this orange one, which acts on some sets of qubits. And this random unitary, let's say it's indistinguishable from Haar. And now we have another random unitary, again indistinguishable from Haar, but now acts on another set of qubits. So it extended all the way there and extends all the way here. The 2 random unitary only overlaps on a very small region, like the middle region. The gluing lemma says the following. It says that as long as they overlap on roughly log k over epsilon qubits, then together these random unitaries, it will form another unitary, like another random ensemble of unitary, such that under any k queries to this, it would be at most epsilon indistinguishable from Haar. And note that the k and epsilon dependence is only logarithmic. So we can set k to be extremely large and epsilon to be extremely small, and the number of qubits that they're overlapping is still very small. So how is this gluing lemma useful? It seems like some random fact about unitaries. So the idea is as follows. Essentially, we're going to use this gluing lemma to glue things together and to utilize this to kind of create a very shallow brickwork wall, such that that very shallow circuit will become indistinguishable from Haar. So the first step is we're going to take these 2 blocks, which are just twice the size of their overlap, and then use gluing lemma to show that when we compose them together, this will be epsilon approximate unitary k design, which just means under k queries to this object, it will be at most epsilon distinguishable from Haar. And now we apply gluing lemma again, but now considering this dashed block and this blue block. Applying gluing lemma again and using triangle inequality, we can show that now this 3 block structure will form a 2 epsilon approximate unitary k design. We then apply it again, but now with this bigger 3-layer block with this other guy. So it's 3 epsilon approximate unitary k design. And we can keep growing it. So we can keep gluing this block and then just packing it in this algorithmic fashion. Now at the end, we will, when we now overlay these brickwork structure over the entire n qubit, we can show that together this two-layer brickwork circuit now forms an epsilon approximate unitary k design. And the final step is just to take epsilon to be extremely small and k to be very large. So we take k to be bigger than any polynomial function in n, and then take epsilon to be smaller than any inverse polynomial function in n, so just negligible. If we now consider these epsilon and k and we plug it in, we see that together this thing forms a 1 over pseudo-polynomial approximate unitary pseudo-polynomial design, which basically just means it's indistinguishable from Hall random for any polynomial time algorithm. And furthermore, because of the log factor, if we now plug in the k and epsilon into the log k over epsilon scaling, this is just slightly bigger than log n qubits. So now what it says is that if I consider these small unitaries acting on roughly log n qubits, slightly above it, and now just packing them up in this two-layer brickwork fashion, then together this whole thing, this very shallow thing, will now become indistinguishable from Hall random unitary. So by utilizing gluing lemma in this kind of composed fashion, we can show that if we have these small blocks that are indistinguishable from Hall, then the whole thing will be indistinguishable from Hall. This is a more formal statement that says if we compose some small Hall random unitaries over log nk over epsilon qubits, it will form epsilon approximate unitary k design over n qubits. So how can we use this object? Essentially, we're going to replace these small Hall random unitaries with either designs or PRUs. So let's say we have replaced them using designs. And now we can get the theorem A. So this theorem says random unitary k design can be generated in just k log n time on any geometry, including 1D lines. And prior to this, the best known was k times n. So one needs a linear scaling in n in order to generate k design. But now that n scaling, n factor has been improved exponentially. If we replace these small Hall random unitaries with PRUs, like this PFC construction that I mentioned earlier, then now we get this other theorem. It says that pseudo-random unitaries can be generated in just poly log n time on any geometry, including 1D lines. So now I would like to tie this theorem back into the previous results to show that those results can be formally proven. And also note that previously we don't even know if PRUs exist. So together these two works essentially show that both first they exist, and second they can be generated in very short amount of time. So one thing to note is that these PRUs corresponds to quantum circuits or time-dependent Hamiltonian dynamics that are shallow, so it has very low complexity, and can only create local entanglement. Because let's say we have a 1D line, and in just poly log n time, we cannot entangle things too much. So it's a highly localized entanglement. However, the strange thing is that they are computationally indistinguishable from exponentially complex unitaries. And utilizing that theorem, we immediately get this, using that theorem B, we immediately get the theorem 1, which says that no polynomial time quantum agent can tell apart poly log n versus exponential n time 1D quantum dynamics. So our first claim. And furthermore, if one notes that the theorem holds on any geometry. So essentially we can compare between, let's say, some 2D geometry with some long-range interacting geometry, like all-to-all-connected geometry. Then immediately we can get this other theorem, which says that no polynomial time quantum agents can tell apart between these short-range interacting or long-range interacting dynamics, which implies that causal structure are hard to learn. And finally, one should also note that the theorem states that can be used in the following way. If we now take these PRUs that can be generated in a very short time and apply it onto any arbitrary state, for example, either product state or toric or ground state, what it will essentially do is, because these shallow circuits are indistinguishable from Hall random, and it's well known that Hall random applied onto any state will turn the state into a Hall random state, which are exponentially complex. These shallow random circuits can turn any state to look like these Hall random exponentially complex states by just adding a tiny bit of complexity to it. And that's how we establish that topological order are hard to learn and no polynomial time quantum algorithm can learn any properties that are invariant under shallow circuits. So together, using these series of ideas, we can establish the hardness of learning time, causal structure, topological order, and actually following our work, there have been various new results showing the unlearnability of all kinds of other phenomena. For example, a new faculty, Yihui, has utilized some of the techniques to show that some features of chaos, of quantum chaos, is actually unlearnable, for example. So now to conclude, we proved that random unitary designs and PRUs can be generated in extremely low depths on any geometry, including 1D lines. And as a result, many basic physical quantities one can show are provably hard to learn. Some examples include the evolution time, causality, topological order, etc. And this poses further questions about, now even some of these basic quantities are hard to learn, what are some other fundamental physical properties that are provably invisible to us, or somehow there's a way to just easily hide them, and there's no way for experimentalists or to design experiments that can learn them and see them. So there is a very interesting follow-up work by Ackers, Boland, Chen, Collar, Mecker, and Bassarani, where they look at a very fundamental aspect, which is there a black hole in the space-time region? So they imagine having a quantum agent that sits on the boundary of some space-time region, so it can perform all kinds of quantum computation on the boundary that encloses certain space-time region. And let's say inside that space-time region, it either contains a black hole or there's nothing. And the agent is just trying to distinguish between these two very different scenarios. And what they essentially found is that utilizing these low-depth PRU construction that we have cooked up and combining with ideas from tensor network toy models of ADS-CFT, they were able to show that a quantum agent sitting on the boundary would not be able to distinguish whether a space-time region contains a black hole or not. And furthermore, their result generalizes to all kinds of other space-time geometries. So one can compare either contains one black hole or two black holes, or contains nothing or a star, etc. And all of these can be shown to be indistinguishable. Which raises some controversial questions, such as, does it mean that event horizon can arise without having a black holes in it? Because if it's either a void or there's a star inside of it, and somehow this agent cannot see it, that means there's some kind of event horizon arising, but there's no black hole. And furthermore, one can imagine that if the agent just goes into the region and then check whether there's black hole or whether there's a star, then wouldn't it just be able to see, distinguish the two? So does that somehow imply that quantum gravity can break some very hard cryptographic assumption that we utilize in proving the existence of these shallow PRUs? Of course, people can also argue that somehow somewhere in their proof it was wrong. I was talking to some physicists that doesn't believe these results, and they said, yeah, they made some mistake. It was wrong. But I think mathematically it seems correct. But it could be that some assumptions regarding some ADS-CFT tensor network toy model might be unrealistic. So I would say there's still more to be done in this area. And that's it for my talk. Thank you so much for listening.